In this video I will explain to you how a transistor works, a very simple NPN transistor. We will look at why it's so important in electronics and also how we can use it in a first operating mode as a switch to trigger a light-emitting diode on and off. I will show you how to build a transistor circuit and also, above all, how you can calculate the resistance values which we use to put before the base and also the collector of the transistor, and we are going to do so in order to limit the current flow and also to adjust the current flow. And in order to solve for these values, we will be using Ohm's law and also the mesh rule by Kirchhoff, which we have looked at before. If you have any questions, drop them in the comment section down below so I can get back to you. And now have fun with the video. I am quite sure that you have probably heard of the transistor before. It's one of the most important components which we have in electronics. It's actually used billions of times in your computers, in your smartphone, as a switch in many cases to process digital information. It also has other uses, as an amplifier, for example. And the goal in this video is to get to briefly know this very important component and also in a small simulation to use it as a switch to trigger off and on an LED. And in order to do this, we're going to look at what a transistor actually is. We're going to look at the input characteristic curve. We will set up and solve equations for this operation as a switch. And finally, lastly, we are going to simulate a transistor as an LED switch using a simulation program. Now, in a nutshell, what is a transistor actually? It's a semiconductor component which is used in computers, in communications engineering, and also in power electronics and many, many other places all around the electronics world. And the transistor is an abbreviation of transfer resistor. This is where the name comes from. And it's a resistor that can be controlled by electrical voltage or current. So we have a voltage or current flow, and this controls the amount of resistance which the transistor puts up against the current flow. And two of the most common transistor modes which we have are digital switching on and off, which is also the topic of this video here, and also signal amplification. And here you can see a few transistors, some of them very small, others rather large, and these metal plates here are heat conducting elements, because in some cases when the transistor switches a lot of power, then we have a significant amount of heat dissipation, and in order to avoid damage to the component, they need these metal plates to conduct away the heat. And that's the circuit symbol here for the NPN transistor. The letters here stand for collector, base, and emitter, and this little arrowhead here gives you the flow direction of current. And the functionality, very brief, is we have no current flow between between collector and emitter when the base voltage is low or below a threshold, and as soon as the base voltage surpasses a certain threshold, this path here from collector to emitter becomes conductant, and then we can observe a current flow. So the base controls the current flow between collector and emitter, hence this symbol here. We have seen other semiconductor elements before, for example the diode, which is also made up of semiconducting components, and in one part you can see the diode here, the diode symbol. We have used LEDs before, but this is not a light-emitting diode. It's simply a diode which lets current pass in a certain direction, and this is made up of two components which are called P and N, and the P part has a shortage of electrons and the N part has an excess of electrons. And the way this is reached, this behavioral property, is by doting the semiconductor material with some elements which make it impure. For example, arsenic is used to do this, and other materials. We will look at these in further detail in upcoming videos, but for now what you need to know is this transition here between P and N is the direction in which the diode is permeable to current flow. So if we connect a power source to the diode, plus on the left and minus on the right, plus on the P side, minus on the N side, then we can observe a current flow through the diode material. And due to this layering, we have this property that if we reverse the polarity, which we can see here, plus on the right and minus on the left, this diode will block current flow in the opposite direction. This is the basic property of a diode. And with a light-emitting diode, we also have the emission of light, but in this case, it's basically only for blocking current flow in one direction. On the right hand side here, on the right side, you can see the transistor, which is nothing more in principle than several of these negative and positive layers connected to each other. We have two, in the case of the NPN transistor, we have two N's on the left and right and a P in the middle, which is the base. Here's the circuit symbol, which we have discussed on the previous slide. And if the base has no connection to voltage, and we only have, let's say, positive connected to the collector and negative connected to the emitter, no current is going to pass through this P section here. And as soon as we put a sufficient voltage level to the base, then this part between N and P and N becomes conductive, and then we can observe a current flow from the collector to the emitter. So the transistor has become permeable for current flow as soon as a sufficiently high base voltage has been applied. And in this case, the transistor acts as a switch, because we can use the base to switch on the current flow between collector and emitter. Let's take a look at the transistor input characteristic curves here, which you can see here. On the x-axis you have the voltage between collector and emitter. Here on the right you can see the circuit symbol. Collector is up top, emitter is on the bottom, and UCE is the voltage drop across these 2 points here. And on the y-axis you can see the collector current, which is the current flowing into the transistor and out of the transistor on the other side, even though the current flow out of here is also augmented by the current flow coming in from the left from the base, but nonetheless the current flowing into the transistor is a large part of what's coming out of the transistor on the other side. And in our case, where we want to use the transistor as a switch, we want to maximize the current flowing from the collector into the transistor, because we want to switch on and off the LED in a binary way. And here you can see how this is actually possible. The blue curves they stand for certain amounts of base current flow. So if we have a base current flow of, let's say, 20 milliamps, this is the behavior you get in terms of collector current. And for a low voltage drop between collector and emitter, the current flow from into the transistor is rather low. But as soon as you increase the current emitter voltage a little bit, the current flow increases depending on the base current. And if you increase the base current, let's say to 40 milliamps or to 60 milliamps, you can see that the basic shape of the curve is rather similar, and this steep slope shows that this strong increase of current flow is happening on the first few, let's say, volts of this current emitter curve here. And what we want to do is we want to get in this area here where we have this steep increase, because we want to switch off the transistor when the base current is below a certain threshold, when it's 0, and we want to switch it on to maximum current flow as soon as we have this base current flow. And in order to get into this saturation area here, we want to have UCE, the voltage drop between collector and emitter, as small as possible. So somewhere here in this area where we start out with these curves. So for a signal voltage US, we want to see a current flow of 20 milliamps into the transistor and thus through the LED. And the first step, the LED resistor, this one here up top, is going to be determined. And then once we have this, we want to determine the base resistance value, this one here, which controls the current flow into the transistor from the base. And in order to get there, we require various values, amongst which are UB and US. This is the supply language here, the supply voltage of the circuit. This is the signal voltage which triggers the base. And also we require the data sheet of the transistor to look up a few values. Now let's start with setting up the mesh equation for the path from the supply voltage down to ground level. We're going to use Kirchhoff's mesh rule to do this, or loop rule. We start with the supply voltage UB, then we subtract the voltage across this resistor here, then we subtract the voltage across the LED, and then also we subtract the voltage drop between the collector emitter path, which is all equal to 0 here. And then we can insert, by using Ohm's law, the resistance, the product of resistance value across the in front of the LED, and also the current flow, which is IC, and then solve for this resistance value here, which is what we need in order to get the required resistance value to protect the LED from too much current. In order to solve or to get the numerical value for this resistor here, let's take a look at what we have. We have the supply voltage. In case of a 9-volt battery, this would be the 9 volts. Then we have the voltage drop across the LED, which is approximately 2.1 volts as soon as it's conductive. We also have the collector current, which we want to limit to 20 milliamps. And what's missing is the collector emitter voltage, and for this we need the data sheet of the transistor. Now here on the right you can see our diagram again, the characteristic curves of the transistor. On the x-axis, this is the voltage which we are looking for. And what we are going to do now is we're going to look into the data sheet of a transistor which we often find in practice, which is the BC547B, a typical NPN transistor. And for a base current of 0.5 milliamps, we have a current flow from in the collector emitter path of 10 milliamps. And the typical voltage of the on the collector emitter path is 0.09 volts. This is the level we can see here. And as we need 20 milliamps, we can extrapolate, which gives us approximately 0.1 volts for a collector current flow of 20 milliamps. But remember that if you, for example, do this in a simulation on Tinkercad where you cannot adjust these values, these are only rough guidelines in terms of how your respective transistor is going to behave in practice. This is only an indication, and you shouldn't rely on this theoretical value. You should always make experiments. But as soon as we have extracted this value here, we can insert it into the equation: 9 volts minus 0.1 volts minus 2.1 volts divided by 20 milliamps, and this leads us to a resistor value of 340 ohms here. And this is the value we need to choose for our transistor, which protects the LED from too much current when we connect it to a 9-volt block battery. Now let's determine the base resistance in the next step here. The base resistance is this one here. We can again use Kirchhoff's mesh rule to do this. We start with the signal voltage here, then we subtract the voltage dropping across this base resistor here, then we subtract the voltage dropping between base and emitter, and this all equals to 0. We can again insert, use Ohm's law to replace U base with a product of R base and the base current flow, and then solve for the base resistance here. R base equals the signal voltage minus the voltage drop across base and emitter divided by the base current flow. And now what we need to integrate here is another property of the transistor. There is a relationship between the current flow from collector to emitter and also the base current flow, and this is called current amplification, and it's often abbreviated with HFE. And this factor shows us that if we use a certain base current flow, the current flow from collector to emitter is magnified, is amplified, and this is the amplification factor here. And if we insert this equation here for the base current, what we get is this equation here for the base resistor. So we have to assume a certain amplification level for our transistor, and we have to insert the rest of the values here to arrive at an estimate on the appropriate base resistance. Now, if we look into the data sheet once more, what we get is a base emitter voltage drop of roughly 0.72 volts for a current flow into the collector of 20 milliamps, and also a range for the DC current gain, this gain factor here, this amplification factor HFE, which we assume to be at 450. It can even be at 200. from times to times, and in order to introduce a safety margin, safety distance, we set it to 450, which is the upper end of the spectrum here given by this data sheet here. And if we insert these values, what we get is a base resistor of 186.3 kilo ohms, which we need to adjust our equation to in order to get the desired behavior. Now let's look at this simulation here. What you can see here is the transistor. We have our LED resistor with 340 ohms. We have our base resistor of 186.3 kilo ohms. We have 9-volt power supply on the left. If we enter all these values correctly, as we have just computed them using our equations, we can see that the current flow through the LED is roughly at 20 milliamps, and also the current flow through the base is as we have expected it to be. We expect it to be 44.4 microamps, and now it's here in the simulation at 44.82 microamps. And this is very close to what we expect. So the simulation shows that our formulas, that they work correctly. Now let's summarize the major findings here from this video. First, a transistor is a semiconductor component which can be operated as an amplifier or a switch. And in order to operate it as a switch, the transistor must be maximally conductive, which means we need to operate it in the saturation region when a certain base current flows. And thirdly, the parameters for this case here, they depend on the transistor type, and also they can be found in the data sheet of the respective component. And without knowledge of the internal structure, all necessary parameters can be determined using the mesh rule of Kirchhoff and also Ohm's law. So we don't actually need to know that much about the transistor in order to use it as a component in our circuit. A small note of warning here: if not an LED but an inductive load is switched, for example a motor or a relay, you must use a protective diode in parallel to the load in order to prevent damage to the circuit. This is something which we will investigate in a future video. But when you trigger, let's say, a relay which switches something and then you switch it off again, the energy stored within the magnetic field of the relay will backfire by means of induction and induce a very high voltage peak into your circuit, which can damage the transistor. And in order to account for this, we need an LED in order to filter out this undesired behavior. That's all for now. If you have any questions, drop them into the comment section down below so I can get back to you. And now have a nice day. See you next time here on The Fearless Engineer.